Hello, Physics 212. This is Matthew here, doing the recording for Exam 2 practice. This is the Exam 2 file on Canvas, the fall 2015 file. This is broken up into 11 multiple choice and some longer problems. So I plan on making at least 2 videos, probably doing all of the multiple choice in one video, and then all of the long problems in a second video. This is a raw recording. I'm not editing anything, so I will probably make a bunch of mistakes, so bear with me. And I will try to include timestamps on YouTube for the problems. Alright, so starting right at the beginning, I'm starting at question 1. It gives us these equipotential lines. Equipotential meaning of similar voltage, of the same voltage actually. And let me just draw these all out real quick. So we have 10 volts here, 20 volts here, 30, 40, 50, and 60 volts. Let me scroll up to give myself some room. We have these points here, A on the 40, we have C, we have B, we have D. And we are looking at question 1. Question 1 is asking the first part, part A, what is the direction of the electric field at point B? We're looking at point B here. It's on the 40 voltage line. And we know with electric field goes perpendicular to equipotential lines, right? So if these are equipotential lines of a constant voltage, our electric field goes perpendicular to them. And finding the direction of our electric field, we know our electric field flows from high to low voltage. So in general, through this set of lines, my electric field is going perpendicular, starting at 60 going to 10, so it is increasing as we move to lower voltage. At point B, we're looking here, point B, our electric field is going to be pointing from high to low and perpendicular to the line at point B. This is our electric field at point B, which is choice G for number 1A, just if you're keeping track of multiple choice. And we want to know, where is the magnitude of the electric field the largest? So when is the electric field the largest? Well, I kind of drew these lines not exactly correctly, but if we're looking on the actual test itself, these lines are closer together. As we move this way, our electric field lines spread further away. So our electric field is the largest when our equipotential lines are closest together. And you're probably wondering why would that be true? We know that the relationship between our electric field and our voltage, electric field is the negative derivative of voltage with respect to distance or displacement. We know that when our delta V is the biggest with respect to R, our electric field, in not including magnitude, is the smallest. But if we're looking at magnitude, because that's what it's asking, where is the magnitude of our electric field the largest, we can simply say our electric field is equal to our change in voltage over our change in R. And I'm just canceling out these derivatives, just saying they're changes, because we're just looking at changes right now. Our delta V, when our delta V changes the most, our electric field will be the biggest. And in other words, electric field is proportional to the change in voltage. Since these lines are closer together, this displacement between them, delta R, is smaller than it would be, say, over here. So with that being said, our delta V with respect to delta R is the biggest when these lines are closer. Therefore, at point A, our electric field is the largest. So I'm going to write E is the largest. Alright, and that concludes problem 1. So all we did is we analyzed direction of our electric field, and we kind of looked at magnitudes a little bit. And you should be comfortable with a setup like this, calculating changes in potential energy, which we know change in potential energy, delta U, is just Q delta V. Right, and say we put a charge here at A and it traveled to B, we could easily calculate our delta V, calculate our Q, and you could calculate all sorts of different things from that. Alright, so moving on to the next problem. We're looking at SI units. We're looking at the SI units for resistance. And the problem does it in newtons, meters, seconds, and coulombs. We could even break it down further if we wanted. So starting with this, we have our resistance, right? And we know a few relationships between resistance and some other variables. So for example, V equals IR, technically delta V, but I'm just going to leave it in volts. And solving this for R, we get V over I equals R. And just for proper notation, I'm going to put brackets here to imply that I'm focusing on the units. And of course, we know resistance is in ohms. Volts, if you don't remember volts, well, you can remember this equation, U equals Q delta V. Solving things for delta V, you get U over Q. U is potential energy, so U is in joules. Q is charge, or coulombs. So a volt is a joule per coulomb. Now doing units, we have volts. What we just said is joules per coulomb. Current, if you don't remember current, we know I, current, is the change in charge with respect to time. So the units are just coulombs per second, which is what we have here. I is coulombs per second, and then this equals an ohm. So simplifying this, you'll get, I'll get my brackets, joules times seconds over coulombs squared. And then we want this in terms of newtons and meters. Remember that a joule is a newton times a meter. So we have a newton times a meter times a second over coulomb squared. And of course, you could keep breaking this up. You could break up the newton into kilogram times a meter per second squared if you were asked to do that. All right, moving on to problem 3. So 3, we're given this arrangement of charges. We have a negative 3q charge in the top left corner. We have a positive 2q in this corner. Here we have a positive 2q. And over here, we have a negative q. And we're given this point P in the middle. Right in the middle of this square. And we are given these distances D. And we are asked to know, what is the electric potential at point P? Well, if we remind ourselves of electric potential is just a fancy way of saying voltage, which is just our K, our constant, times Q over R. Now, if we're looking at this, we have 4 charges, right? We have these 4 in the corners. We're given the distances, so this just becomes just plugging in and calculating our electric potential. So voltage, I'm going to go to this top left charge first. It's negative 3, right, for our Q, negative 3Q times K. So negative 3KQ over our distance. Our distance is D. For the second charge, we have 2KQ. This should be a capital Q. 2KQ over D. For this bottom right charge, we have negative KQ over D. And for this bottom left charge, we have 2KQ over D. And then simplifying this, we will actually get 0, right? We have negative 3 minus 1, factoring out that KQ over D. Negative 3 plus 2 minus 1 plus 2. That just equals 0. So our voltage at the center of this configuration is 0. All right. And part B for this question is asking, what is the magnitude of our electric field at this point? So now, if we're referring back to our knowledge from exam 1, let's just draw our electric field lines. I'm just going to draw the lines. Let me call these 1, 2, 3, and 4 just to avoid confusion. So this is electric field 1. This is a positive charge, so electric field 2. This is a positive charge, electric field 3. And this is negative charge, electric field 4. Now I'm looking at this and I can say, look, I have a 2q charge over here, I have a 2q charge over here. If I were to tilt my coordinate system, say like this, where this line's parallel to this axis, I can say the electric field from this positive 2q charge and this positive 2q charge will just cancel out. So what does that mean for me? I only have to focus on this negative 3q charge and this negative q charge. And because I picked my coordinate system as such, I don't have to worry about unit vectors or anything like that. I could leave my coordinate system normal and I should still get the same answer. So I'm just going to do it with the tilted coordinate system. I could say EY. I don't really need to worry about direction. The problem doesn't ask for it, and everything's all in one direction, in the y direction. So my electric field, keeping in mind that I already picked the directions for my electric field based off of the physical meaning of these charges, meaning this is negative or positive. If it's negative, the electric field goes towards it. If it's positive, the electric field goes away from it. So, using my coordinate system, this electric field 1, is in the positive direction. So I have k times my charge. My charge is negative 3k or negative 3q. Again, I already account for direction, so I'm going to leave it positive. My distance is d. It's d squared, right? Because our electric field is k times q over r squared. And then my E4 is in the negative y direction, so I'm going to leave that negative and then not have to worry about anything with the sign of the charge. I already accounted for it. So k times q over d squared. And simplifying this, you'll just get 2k q over d squared. All right, moving on to question 4. Let me just clear this quick if it lets me. And it does. All right, awesome. Let me just draw my circuit here. I have a capacitor. My capacitor is at 3 microfarads for its capacitance. I have a 4 ohm resistor. And I have an 18 volt EMF. My problem statement tells me an initially uncharged capacitor is connected in series with the resistor. This is initially uncharged. There's no charge, which means there's no voltage drop across this initially. And it says, at a certain time, the charge on the capacitor is 6 microfarads, or 6 microcoulombs, sorry. 6 microcoulombs. And I want to know what is the current in the resistor at this time. Okay. Well, I'm given my charge, and I'm given my capacitance. We know relating those can give us our voltage drop across our capacitor. We know that Q equals C delta V. And solving for delta V is what we're interested in. Delta V equals Q over C. And these are in the same prefix units, meaning we don't have to worry about unit conversions. We will just get 6 over 3 equals 2 volts. That is the voltage drop across my capacitor. So I'm going to write that in purple here. The voltage drop across my capacitor at this time is 2 volts. And I want to know the current in the resistor. Well, let me just draw a basic current loop. This is what I'm assuming my direction of current is. Not that it matters, because we just want to know the magnitude. It's not defined as a given direction, so I'm picking an arbitrary one. And now I'm going to do Kirchhoff's voltage loop rule, meaning sum of the voltage drops across the loop has to equal 0. So starting with this battery and using passive sign convention, meaning I'm paying attention to the direction of the current through my different objects, I have an 18 volt EMF. Actually, let me write this out conceptual first. I have my EMF, E. I'm going around. I have this capacitor, right? This capacitor, because of the charge distribution, And let me make that blue because it's positive. I have positive here, negative here. My voltage drop is negative due to passive sign convention, meaning that my voltage drop when I'm adding it will be negative delta V. And I'm going to call it sub C for capacitor. And then I have my resistor. Remember, with current going through it, current goes as such, meaning that if we're looking at this resistor itself, the top end of the resistor is at a higher voltage than the negative end. So I'm going to say minus delta VR, and that all equals 0. Simplifying this a little more, just breaking that delta VR up, we know delta V of a resistor is I times R equals 0. And we want to know I. So solving this, and I like to solve everything symbolically first before I plug anything in. It's a lot easier to catch any mistakes. Solving this, I get I equals EMF minus delta VC over R. And plugging everything in, my EMF is 18, my voltage drop across my capacitor is 2, and my resistance is 4, which gives me that my current is 4 amps. Current is 4 amps. So what we did in this problem is we were given charge and capacitance. We know we have to relate sum of voltage drops across the loop in order to find a current. That's what we've been doing these past couple weeks. So I decided to find the voltage drop across this capacitor. I then summed my voltages up, found my current, and I was done. Alright, so this concludes the first segment of my series of videos. I will be posting the next video shortly. So see you then.